lives. And so that's going to be a major topic today. Our first speaker is Vineth, and I hope I get your name right, Balasubramanian. And he's going to, he is the head and associate professor of the computing department at the Indian Institute of Technology at Hyderabad. He did his PhD at Arizona State and has research interests in deep learning and machine learning, optimization and real world applications. And today he's going to talk to us about relationships between robustness and explainability. And this is a theme that especially resonates with me and also with what we've been doing over here in France at ANITI at our 3AI Institute. We really do see a connection between interpretability and robustness. Many of the same techniques that we use to check for robustness also have an application in explainability, and also have some links to issues like fairness and bias that we'll hear about later in this workshop, I think. So Vineth, if you can share your screen.
Hopefully you can see my screen and hear me.
We see you and hear you.
Perfect. Thank you. Thank you very much, Nicholas, for the kind introduction, and KV for the invitation to this interesting workshop. So as Nicholas just mentioned, my talk today would be on connections between explainability and robustness of neural network models, something that we've been exploring in the last 2-3 years. So I'll try to talk about a couple of efforts in this direction, and probably even talk about maybe some larger questions to answer in the context of both these topics. Before we move forward, maybe I know that since this effort is about enhancing collaborations between India and France, just a quick background about myself and my research group here. We broadly work on machine learning, deep learning, computer vision. And among our problems of interest, there are primarily two directions. One is on explainable deep learning, in which we've been looking at causality in explainable deep learning in general, which would have been another topic that I would love to share my work on. But today I'm going to focus on explainability and robustness. We've also been looking at explainability in computer vision, so on and so forth. On the other side, we've been looking at learning with limited supervision topics such as continual learning, few-shot learning, zero-shot learning, and probably even mixtures and variants of all of them over the last few years.
Well, you have to come visit us then, Vineth, because we're interested in exactly these topics.
Oh, wonderful. Thank you. I'd love to talk more. So coming to the topic for today's talk, it's going to be at the intersection of adversarial robustness and explainability. And to start with, just a very brief introduction. I'm quite sure everybody in the audience is aware, but adversarial perturbations are about adding imperceptible perturbations to an input, leading to a wrong model prediction. Over the years, there have been quite a few attacks that people have developed, FGSM being one of the earliest in 2015, which is the gradient sign method. Then you have an iterative method such as PGD, projected gradient descent, which came up later in 2018, and many more methods over the last few years, to be honest. This is not exhaustive by any means. All of them aim at adding some form of the gradient to your original image, thus changing the model prediction, although the perturbation by itself is not perceptible to the human. So one way to counter adversarial perturbations, the most popular way today, is known as adversarial training, where you make models robust by augmenting training data with adversarial perturbations. To some extent, you're trying to make your model familiar with what could be an adversarial test distribution during training itself. And it's typically done by adding one more maximization loop inside your typical minimization problem. And popular methods in this direction are using adversarial training using PGD, projected gradient descent, as well as methods such as trades, which was proposed in ICML of 2019. So I'm quite sure most of you are aware about these. On the other hand, a very limited view of explainability in neural network models is I think explainability is a very vast space today. It also is a very subjectively defined space today. I think it depends on what somebody views as explainability. So I think there's a lot of variation in how people view explainability in general. But a more well accepted definition is in terms of attribution or effect of an input variable on an output variable. Whether that is really explainability, I think is debatable, but I think that's the largely accepted view at this point in time, largely followed view at this point in time. In terms of methods itself, I mean, a lot of my examples would be computer vision focused because that's where I come from, but I think methods wise, all of these apply to any other kind of data type. It need not be just computer vision, but I think a lot of these, especially adversarial perturbations, have emanated from image-based attacks. Similarly, in terms of explainability, the methods so far are largely, you could say, gradient-based methods. In this, there are a variety of methods that have been developed over the last few years. Most of them try to understand the importance of each pixel by extending your chain rule. Like when you backpropagate, instead of computing derivative with your respect to your weights, you compute your derivative of your loss or error with respect to your input by just extending the chain rule. That gives you an estimate of the attribution of an input towards the output. There are methods such as guided backprop, smooth grad, integrated gradients, so on and so forth. Then you also have methods which use gradients again, but they probably use activations of convolutional layers or other layers inside the neural network to understand how a neural network arrived at a particular decision, or which aspect of an image or which aspect of an input resulted in a particular outcome. So you have methods such as CAM, GradCam, so on and so forth. GradCam++ was one of our methods in visual explanations here. More recently, there has also been an interest towards Shapley value methods here, where you look at the importance of a variable or a pixel as an expectation of a value function of adding a variable to all possible coalitions of other input variables, the game theoretic approach. This is a lot of this. One of the earliest papers in this space was called Deep Shack, which was published in 2017. But over the last few years, there have been many variants that have been developed over Shapley value methods. But at the end of the day, the value function that's used here is again often gradient based. So at the end of the day, I think most of these explainability methods rely on the gradient of the loss with respect to, could be any layer of a neural network or the input of a neural network to arrive at attribution or explainability. Yeah, as I said, there's perhaps a limited view of what explainability is. There's a lot more today, but I think in terms of methods, perhaps these are the most dominant methods that are used today. So with that very brief introduction to adversarial perturbations and perhaps explainability, if we had to think deeper as to what could really be causing adversarial robustness, there are a few papers. I don't think there is a very convincing answer to this question. But a couple of interesting papers that have come in the last few years there is this paper called Adversarial Examples Are Not Bugs, But Features, that was published in Europe of 2019, which argued that adversarial examples can be attributed to presence of non-robust features. That means features that are derived from patterns in data that are predictive, but brittle and incomprehensible to the humans. So you could perhaps extend this to say that these are perhaps some spurious correlations. So there are some correlations between input and output, which the model latches onto, but those correlations are not really representative of the semantics in the relationship between input and output. That's one direction in which people say that's what could be resulting in adversarial perturbations, adversarial attacks, so on and so forth. But there was an interesting counter to this paper that was published soon after. I think this first work came in about May of 2019 on Archive. And in August of 2019, there was a retort to this first paper, which said that there are adversarial examples, which are also just bugs, which are aberrations in the classifier that are not intrinsic properties of the data distribution. So in a sense, this seemed like a claim and a counterclaim. But from a different perspective, I think they both say the same thing. I think both of them seem to be claiming that adversarial examples are some things that don't represent the true relationship between input and output that we seek to capture in whatever sense, be it in terms of features or be it in terms of aberrations in the classifier, in the model itself. I think that's essentially what both of these are trying to convey. So I think there have also been other studies on the connection between adversarial robustness and generalization. Is it really possible to generalize if you were susceptible to adversarial perturbations? Because the common example that people relate this to is humans, because we don't easily, if a small Gaussian noise is added to an image, the human brain can still kind of perhaps smoothen over it, and we don't fall for a different prediction for that particular input. So while the human brain perhaps can be fairly generalizable, why is it that these models are not generalizable in this sense is still an open question. We still don't know why this happens. I think there are different theories, but we don't know why this happens. So the way we were trying to approach this problem, we started this work, I think, a couple of years ago, and we were trying to look at whether explainability could be the cue for adversarial robustness. And if you take this very popular example that people give for adversarial robustness, this is one of the standard images that people use to explain adversarial perturbation. So you have an original image, which was predicted by one of the well-known models as a temple with a 97% confidence, which is say the softmax output. If you add some gradient perturbations to it, now the same model predicts this as an ostrich with 98% confidence. So this is broadly the problem with adversarial attacks. The question that we try to ask is, okay, if this be the case, can the model really explain both decisions effectively? It's quite evident that it could perhaps explain one of these models. Let's say if it depending on what explanations mean to an end user. Currently, the way people look at explanations is to say that it's looking at the set of pixels surrounding the temple here, and hence calling it a temple. If that be the case, the model cannot really give the same explanation for both of these images and still be able to predict different labels. So it's pretty intuitive here to understand that there is no sane way to actually explain both outcomes meaningfully. This clearly directly points to a connection between explainability and robustness, because they almost seem complementary to some extent. If you maximize some measurable outcome of explainability, perhaps your robustness also should increase. That's perhaps inherent from such an intuitive example. So we tried to start this work, and when we started this work a couple of years ago, I think there were not too much work at the intersection, but a few different papers which we list here. There was a work in 2018 which said that they tried to understand the connection between how good the saliency maps were or the explanations were if you made your models to be adversarially robust. And they observed that robust models are more biased towards image shape than its texture, and hence give better saliency maps, which seem to be one of the issues with traditional models, that if a model can be easily attacked, they probably rely on some form of texture in the image, not necessarily the shape. And that's the reason why it's easy to perturb a few pixels and the texture changes a little bit. And now the model starts predicting a different label. So they argued, or rather just observed, that robust models are more biased towards image shape. Etman and ICML of 2018, they tried to quantify this behavior by considering the alignment between the saliency map and the image as a metric for interpretability. They say that how closely a saliency map is aligned to an image. When they say image, they mean just the object in the image, because they considered simple data sets like MNIST there. And they use that as a metric for interpretability. And they actually show a simple connection between robustness and interpretability there. Then a couple of other works that came in 2019 tried to extend this line of thought and asked whether explanations themselves can be vulnerable to attacks too. In fact, that's one direction where we have been exploring a few things over the last couple of years too. I'll probably talk about that also today. And they also tried to ask whether robust and interpretable saliency maps imply adversarial robustness. So if you had robust saliency maps, does that imply adversarial robustness?
Yeah, I have a question. I have just a question here.
Sure.
Yeah, I mean, do you plan to formalize what explainability is? Robustness, I kind of understand, but what is explainability? Will you formalize that? If you plan to formalize, I will not ask, I'll wait. But I don't know what explainability is, if you could.
Sure. Thank you for the question. So I don't think there's a very clear formal definition for explainability in general. So today, explainability is understood as most metrics for explainability are heuristic or showing to a human and trying to see whether the explanation really makes sense with respect to what the user perceives of the image or so on and so forth. But very simply speaking, going back to what I had earlier, the gradient of the error with respect to the image is often considered the explanation. In some sense, the attribution is considered the explanation. So I don't want to get into this too much, but these days people argue on the difference between what is called interpretability and explainability. Interpretability is considered as attribution, which is the effect of an input variable and an output variable. And explanation is more considered as transparency of a system. How easily can you follow how it arrived at a decision, say a decision tree, for instance. Whereas interpretability is more the attribution. I think I'm trying to avoid getting into those nuances because it's sometimes confusing. I don't think there's clear agreement on a formalization for explainability in that context. But I think for this talk, I'm assuming explainability to be largely attribution, which is the effect of an input variable on an output variable.
Yeah, I think we can come back and revisit this in the discussion, because this is a very general question, Mandayam, that is going to really impact several of the talks.
Okay. And I think there's also a lot of subjectivity in that topic too. So yeah, maybe let me go ahead and complete it, and I'll be happy to discuss this towards the end. So one of the first efforts that we had was at ECML last year, where we tried to see if we could use explainability for improving adversarial robustness. So let me perhaps describe the method here. So we're considering a neural network phi, which say goes from a d-dimensional data point to k classes, parameterized by weights theta, assuming x is the input, d-dimensional, and there are totally c is the set of classes, where there are totally k number of classes. And we denote saliency map to be a vector s, which is d-dimensional again, has values lying in the interval 0 to 1. And an anomalized saliency map for an input to be given as the gradient of phi I star. Phi is again the output of the neural network. I star is the predicted label of the neural network, and grad with respect to x. That's what is the saliency map. So for practical purposes, this is our explanation in this work. I mean, whether it's not or yes, I think it's arguable. But for practical purposes, this is the explanation for us that we consider in this work. And we define projected gradient descent attack as an iterative multi-step attack, where you initialize x naught to be x, and in each iteration you add some loss to the input and project it onto some feasible space, and you keep iterating over and over again so that you get an x value which maximally perturbs or increases your loss. That's the main idea for PGD attack. And what adversarial training tries to do is to make models adversarially robust by matching the training distribution with the adversarial test distribution. So you have the standard error minimization, empirical risk minimization, but inside the minimization, you also have a maximization loop where you try to find for every x that you give as input to your empirical risk minimizer, you add a perturbation which is found through a PGD attack, which could maximally change the label, and you provide that during training itself. That's the main idea in adversarial training. Now, with this background, what we observe is that adversarial perturbation at any given x is you could consider as an infimum over all your perturbations E, let's say, over all your norms of E, such that the label of your neural network is not the same as the label given the original input x. That's your adversarial perturbation here. So we followed Edmond's work, who showed that for most neural networks, the score function phi can be shown to be locally linear in the neighborhood of x. This happens when your activation functions are largely linear. They show that it works for most practical activation functions. But you have your phi I of x plus your perturbation, adversarial perturbation, to be locally linear in the neighborhood of x. So that's what you have. So based on this, it's quite trivial to see that if you want to find the E such that your argmax over I is different for x plus E and x, you want some phi j of x plus E to be greater than phi I star, which is the true label of x plus E. Now, using this first order expansion here and replacing it into this term, it's once again simple to show that that means the difference in gradients between any other class J and your true class I star should be greater than the difference between your predictions itself. So this automatically points to the fact that you could choose your E to be a multiple of the difference in the gradients between any other class and the true class, which we show in our paper can be practically simplified, can be approximated as just the negative of the gradient with respect to the two class itself. For binary, it's very straightforward. For multi-class, it's a heuristic, but that's what we end up using in practice for as the adversarial perturbation here. Does it really work? We show that just running a projected gradient descent where you don't really use the standard projected gradient descent, but just use the saliency map of the predicted label here, that itself turns out to be a pretty strong attack. And you see that the accuracy significantly starts dropping with this kind of an attack. So it seems to be just using the saliency map and going in the negative direction of that, of the saliency map itself, is a pretty strong attack for many of the neural networks. So based on that, we come up with a methodology for training based on saliencies. So the main thing probably I want to point out, you can ignore the algorithm. The main thing to point out here is this simple expression where we show that what we actually do is, it's possible that when you're training a neural network in your initial iterations, your saliency map is not strong enough. It may not point to the right areas of the object that correspond to the output because the model is still learning. So what we do is we use our perturbation to be a random vector with a certain probability, and the negative of the saliency map with a certain probability. And the probability of choosing the saliency map keeps increasing over the iterations t. So that's why you see a factor of t here. So that's what we end up doing for our saliency-based adversarial training methodology. The rest of it stays very similar. So we use that to obtain your samples during empirical risk minimization. So I think I won't go through these numbers here. Obviously, we got decent results with this kind of an approach. We show this with different kind of, we show it on its own. We show it as a combination with PGD. We show it as a combination with trades, so on and so forth. Interestingly, we also show one of the concerns here could be is, but for this kind of a method, you have to compute the saliency map, okay, which itself computing the gradient can take time. So what we show is if you consider data sets where there is already a bounding box around the object, right? Some of the data sets actually have a bounding box around the object in an image. So which give us a weak sense of a saliency map. So that's anyway part of the image. So we use that straight off the bat to train our neural network. So in this case, you could assume that there is no gradient computation. There is no inner maximization while training. We just use the bounding box, which we consider as a weaker form of saliency map while training. And with that, we are able to actually perform better than some of the adversarial training methods, as you can see on this table. So in fact, we see that we also notice that the saliency maps for robust models, adversarial robust models, are actually stronger than for non-robust models. So we show that if you took those saliency maps and trained, we can even further get improved performance. Okay, I know I have only about 3 minutes, so let me quickly talk about the other direction of this work. So we've also been exploring this going from adversarial robustness to attributional robustness. So in addition to what we are seeing as adversarial robustness, a trustworthy neural network model must produce very similar interpretations for two very similar human indistinguishable images. So there was a paper in AAAI 2019 which showed that it's possible to craft changes in an image which are imperceptible to a human, does not change the model's prediction, but changes the explanations alone. These are called attributional attacks. So since then, we have been looking at several efforts to actually try to see how can you now get attributional robustness? How can you ensure that you can train your model in such a way that the explanations cannot be attacked? I'll probably talk about one of them briefly and then conclude this talk. So we focus on one of the methods that use a gradient-based approach to compute the attribution, which is called integrated gradient. It's considered a seminal method for computing the attribution of an input on the output. It uses a path form of the gradient to compute the gradient. And we define a couple of regularizers while training. One of them called class attribution-based contrastive regularizer, where we try to ensure that while training, we regularize the model to ensure that the true class attribution is far away from what we call as a maximum entropy attribution. A maximum entropy attribution is where all pixels in an image could be equally responsible for the outcome. That's what we call as a maximum entropy attribution. So we try to ensure that the true attributions that we get from the model are as far away from that, and the negative class attributions are as close to a maximum entropy distribution. This is one of the regularizers we introduce. I think I'll skip the other one in the interest of time. It's a bit, it can get a little complicated in terms of how we think through this. If required, maybe I'll come back to this in the discussion. And then based on these regularizers, we now do a very similar step like adversarial training, where we have an outer minimization step and an inner maximization step, which is based on these regularizers, where we find an attack image that's based on these regularizers to address this issue. And using this approach, we show that when you have an image and its perturbation, you can see here that this is the original image and this is the saliency map that's obtained using the integrated gradient method for this particular image. And we see that when you perturb the image, it's human imperceptible. The changes are human imperceptible, but the saliency map completely changes while the model prediction stays the same. And if you look at the rightmost column here, you can see that for our approach, the explanation doesn't change significantly and still focuses on the right pixels while staying with the same prediction too. More recently, in Europe of this year, we had another approach where we tried to see if we could get adversarial robustness without adversarial training, which is perhaps a time-taking exercise, using explanations again, which we have a two-phase approach where we have a teacher model, which is adversarially robust, and we try to ensure that the saliency map of the students of a student network, which is our target network, is as true to the original teacher model as possible. And just by doing this, we find that we actually get a very adversarially robust model. So no inner maximization and no adversarial training, which is perhaps the most costly part of adversarial robustness. And we actually show that we significantly outperform existing models on adversarial robustness using such an approach. Yeah, I know I've probably run out of time, but I'll be happy to discuss some of these in more detail over the Q&A session here. But just to conclude with some open questions and open problems here, I think there's a lot to look at in terms of the intersection between explainability and robustness. Considering the lack of objective evaluation metrics for explainability, a question could be, could robustness become a metric to evaluate explainability? Robustness is measurable, is more measurable than a subjective term like explainability. Is that something to consider? What family of perturbations should have the same explanation? I think this could be something that could be debated too. Is there a duality between maximizing explainability and minimizing vulnerability to adversarial attacks? What space for visual explanations, a feature space or a frequency domain, is most related for robust to robustness? And finally, is there a path to multi-criteria robustness? Because it almost looks like now that if you become robustness on prediction, you could become vulnerable to explanation. So, but we clearly want models that are perhaps robust to multiple criteria and to multiple factors. How do we go towards this becomes an open problem with these kinds of directions. I think I'll stop here and I'll be happy to take questions. Thank you again for your patience and the opportunity to share our research here.
Thank you very much, Vinith, for this very nice talk. Lots of questions that you brought up. So Purushottam, you have a question in the chat. Maybe you want to elaborate on it.
Thanks, Nicholas. So Vinith, hi Vinith. I was wondering in that approach where you were able to very nicely demonstrate that the perturbation vector must align with the difference of the gradient with respect to two classes, one being the correct and the other being the, so that's where with the other class can it be found using techniques like hard negative mining, which are already very common in multi-class learning?
Absolutely. In fact, one of the work that I did not talk about does this. So in this work here in between, that was at ECCB 2020, we actually did something like that. We actually did a triplet kind of a loss, which effectively is like hard negative mining. but in this case, we focused on what we call attributional robustness to improve the robustness of explanations. But I think that's a very nice idea, and that's exactly, at least a version of it is what we use in this particular work.
Thanks, Vineet.
Yeah, thanks. Are there other questions in the audience? If not, I have a question.
Yes.
Okay, so yeah, this idea of attributional attack. As I understand it, what you're doing, I just wanted to go over that to make sure I understand, because it's a worrying kind of thing to me. So you're taking changes or the effects of the saliency map on predictions to be the sort of explanatory link. And then, so what these attributional attacks do is they kind of mess up our intuition about this, because they're changing the explanans without changing the prediction. And so if I got that right, what that seems to point to is, in effect, that maybe this notion of the saliency map as constituting the explanation might not be the right one, because we're getting a decoupling here. Maybe I'm not thinking of this correctly. So Vineet, I have a puzzle more than a question.
Sure, no, thank you. I think it's a very deep question, to be honest. I think it's fundamental. I think this idea of a saliency map can hold for any kind of a data. I mean, effectively, gradient is in some sense a placeholder for the input of an input, effect of an input variable on the output, the attribution. I think perhaps the true answer could be considering causal principles, ensuring that your attribution respects causal relationships. I think a lot of this comes from spurious correlations, which is perhaps the real elephant in the room. But in this particular case, you are right. I mean, it could be. So in fact, very broadly, I'm quite sure you're aware, but very broadly speaking, explainability methods these days are categorized into what are known as post hoc methods and anti hoc methods. Post hoc methods are where you first train a model and later try to explain it, which is what saliency maps try to do, or any other, most other methods too, even Deep Sharp, and all of them try to do the same thing. In fact, Cynthia Rudin, who won the Squirrel AI prize this year, I think she's been vouching for more anti hoc interpretable methods where the explanation can come along with the training itself. It's not something post hoc, because then you're kind of coupling the two rather than decoupling. Because in this case, you're right. Someone could argue that maybe the way I'm computing the gradient to get the saliency map is the problem. Maybe the model is learning the right things. The way I'm computing the gradient is wrong. And it's very difficult to find out where that error could be. I think that does remain as an open problem at this time. But otherwise, you're right. What these attacks do, this issue was firstly discovered in this paper in AAAI 2019, where they showed that they came up with a few different attacks where they showed that with small perturbations, they could keep the model prediction the same, but the explanation changed vastly. So for example, once we all move to trustworthy AI models, hopefully sometime soon, if my company doesn't like some other company, I'll hack them to make them give completely different explanations. And this could be for not just images. So suppose I say that for a risk of in a patient record, the risk of a heart attack is coming from, say, blood group, and which is perhaps true. Now I could hack it to completely start predicting a different variable as attributing the highest risk for a heart attack. So I think this could be a very general thing across different data.
Right. Okay. Well, thank you very much, Vineet. I guess we're going to go on to the next talk. We're going to change gears here. We're going to look at, thank you again, Vineet. And maybe you can stop sharing your screen. And we're now moving to a quite different take on explanations, one coming from a logic-based framework. The talk will be given by João Marques Silva, who's a director of research at the CNRS and also a chair in the Toulouse 3AI Institute, ANITI, which I understand in Sanskrit means disorder, but that's okay. Out of disorder comes creativity. So that's what I'm hoping you'll take away from ANITI. And the title of the talk is Formal Explainable AI. So João, you are here, and so you have the floor.
Okay, good morning, everyone. Well, I presume you can see my slides.
Yes.
Okay, so I will be talking about a very different way of looking at explainability. It's based on formal reasoning methods. So everybody is familiar with the many successes of machine learning, self-driving cars, the many successes of DeepMind, personal digital assistants, image and speech recognition, robotics, and so on. What happens is that, as the previous talk also mentioned, machine learning models are opaque, meaning they are not interpretable. Sometimes the results are correct. In this case, for example, we have a prediction of a cat. But the problem is that we don't know why, in this case, a neural network is predicting a cat, and we don't know which features are important, and whether there are general explanations that we could try to extract. And so this was the original vision of XAI. So at the time, the prediction would be the explanation, and that was not enough, and there was the goal of a more clear explanation. And this is what we have been looking at for the last a few years as well. So there are important reasons for XAI. In Europe, we have since 2016, the GDPR. Some authors believe that GDPR entitles people to explanations. There is also the effort of DARPA in the US on explainable artificial intelligence, and some efforts on having accountability of algorithmic decisions as well. And some authors have put forth important arguments for why explainability is crucial. Also in Europe, there have been more recent efforts on having guidelines for trustworthy AI, and that include, for example, the principle of explicability. Essentially, people are entitled to receive explanations for decisions that are made automatically for them. What we are more interested in is high risk and safety critical applications. So high risk in Europe, at least, there are lots of examples. A few examples are biometric identification and categorization of people, management and operation of critical infrastructure, for example, power, water, and so on, law enforcement as well. And then we have safety critical applications like self-driving cars, autonomous vehicles, and aerial devices, and so on. And in these cases, the correctness of explanations is paramount. They are paramount. They are extremely important because they help to build trust, they help to debug AI systems, and they can prevent accidents that have disastrous consequences. And so this is essentially the motivation for the work that we have been doing. So the outline of the talk is I will try to set up what we are talking about, and try to talk about what we feel are important misconceptions in XAI, then introduce formal XAI, and summarize the progress that we have witnessed in the area. So in this talk, I will talk about a set of features. Each feature takes values from some domain. The domains can be categorical or discrete or real values. And this allows us to define the feature space. And then we have a set of classes, this is standard. And for us, the machine learning model computes a classification function that maps feature space to the classes that we are talking about. An instance is a point in feature space and its associated prediction. And the goal that we are trying to answer is how to compute explanations for an instance, so point and its prediction. We can represent the point also as a set of literals where, so for a given feature I, we have a variable representing the values of the feature, and it's true when that variable takes the value of a complete point in features. So let me talk a little bit about the misconceptions in XAI. So as the previous talk also mentioned, there is a very well-known approach for explainability, which is model agnostic explainers. Two of the most famous are Lime and Chap. The previous talk also mentioned at least one of them. So here the goal is to learn a very simple interpretable model, a linear classifier or decision tree. And essentially we train a classifier either using game theory, as in the case of Chap, or sample based in the case of Lime. Anchor is a different approach. Here the idea is to learn the features that are considered more important for the prediction. And like Lime, Anchor is sample based. Now, I should note that none of these tools, these approaches offer formal guarantees of rigor in the explanations that are computed. A different approach to explanation is what's called intrinsic explainability. So here it's that the model that we learn, the interpretable model that we learn, is considered the explanation. Concrete examples include decision trees, decision lists, and decision sets. So the questions that we have been that we started to ask was, can a model agnostic explainers be trusted? Number one, and the second question is when we do intrinsic explainability, are we getting interpretable results? So let's start first with model agnostic approaches, and this is a very simple example of a boosted tree, with 7 classes, and it's very simple so that it can fit in a slide, right? So in this case, if we plug in the features here, we can essentially pick the class with the highest value, and in this case, it's going to be reptile, which is shown here. So if you plug in the features, you can pick the values, and the one with the highest value will be reptile. So a tool like Anchor, and this is one of the most recent tools for model agnostic explainability, would come out, would run its algorithm and would report these features in boldface, not air, not milk, not fins, as the explanation. And so essentially for us human beings, this means that if these 4 features are true, then the class should be reptile. What we observed a couple of years ago was that this was not true. So the same explanation explains another instance with a different prediction. So if you can have not hair, not milk, not tooth, not fins, and the class be amphibian. And so this is fairly problematic. So essentially what I'm saying is that model agnostic explanations can be sound. So we can have an explanation X, like I showed in the previous slide, and X is consistent with an instance V1, C1, and consistent with an instance V2, C2, and C1 is different from C2. So essentially what we are claiming is that in this case, X is useless. So to make things a little bit more concrete, suppose a bank application, and the explanation, for example, is age 45 and the salary is 50K, and the class 1 is you accept the loan, and the class 2 is you decline the loan. So of course, in this case, it's as I said, X is useless because it does not allow us to understand why the loan is approved or rejected. And we claim that it's not even an explanation. So you could say that that doesn't happen in practice, and what we observe is that actually it happens a lot in practice. So these are examples on some data sets, and this is the percentage of incorrect explanations that we could observe with Lime and Anchor and Sharp, and in some cases it's almost all the time the explanations are incorrect. Okay, and so this is what we observed for model agnostic approaches. We also looked at intrinsic explainability in the concrete case of decision trees. Why? Because, well, for 2 decades, decision trees are considered the example of interpretability. Actually, a very well-known author, Brayman, wrote in 2001 that on interpretability, trees rate an A star. So there is general agreement that decision trees are interpretable. So let me try to convince you otherwise. So suppose you have a classifier, again, as we talked about before, and it is defined, it's a disjunction of the features. And again, the features are Boolean in this case. So if we try to construct a decision tree in this case, any reasonable decision tree algorithm will pick one variable. You can pick the order. So I don't pick the order, you pick the order. So for example, it's xi1. And if it's 1, you have to agree with me that it's going to predict 1. Otherwise, we don't have any information. And so if we have to pick another variable, and we repeat the exercise, and we do this until we have tested all the features. And in the final one, if all of them now are 0, it predicts 0. If this plus 1 is 1, it predicts 1. Okay, and notice that the order, I did not pick it, and someone else, my adversary, picked it. Now, suppose that you have a point in feature space, and notice that we are keeping the order 0, 0, 0, 0, 1. So essentially, it's this path here. Clearly, the prediction is 1. So if we look at the path in the decision tree, we can say that if the first feature is 0, the second is 0, and so on, until the last one is 0, and the last one is 1, then the prediction should be 1. Of course, we know that this is not really necessary. We know that as long as the last one is true, for sure the prediction is going to be true. So what we are saying is that in this concrete example, 2 explanations can be arbitrarily smaller than paths in the decision tree. And so we claim that decision trees are actually not interpretable. And again, of course, all these definitions, there are not rigorous definitions of interpretability. We say that this is the case whenever interpretability correlates with the succinctness of the explanation. And you could say that that was a concocted example. You don't see this in practice, and so we argue otherwise as well. So here is an example of what is called an optimal sparse decision tree from a paper 2 years ago. I showed in the paper actually this example, and we can prove that lots of the examples I showed in the previous slide happen with this example as well. So I just pick one of them to illustrate the point. So suppose the path is this one. So middle is not X, top left is not X, bottom right is X, the bottom left is not X, and top right is X. So essentially it's this path here. And we can a little bit of analysis. So it's immediately clear, since the prediction is 1, the value of middle is irrelevant. If we flip it, we still get 1. Bottom left the same. So essentially this allows us not to ignore middle and bottom left. There is another one which we can drop, which is this one, top left, because since bottom left is true, here if we flip it, we get here as well, and so essentially we don't need this one, and if we flip this one again, this one we have to keep. So essentially what we are saying is that starting from a path with 5 features, we can get a reduced explanation, logically explain a reduced explanation with 2 features. And so the fact that you have an optimal sparse decision tree does not really help you to have succinct explanations. We can get much more succinct explanations by doing the logical analysis of the classifier. In this case, it's the decision tree. So this is what I just said. So we go from 5 literals in the explanation to 2 literals in the explanation. Okay, and actually in this case, we could find the situations like this one in 5 out of 8 passes. So lots of redundant pairs. We call them explanation redundant pairs. And so that's the point I also made. So this is 3 pairs may not be minimal, even if the decision tree is optimal and sparse according to the criteria that was proposed 2 years ago. And in a more recent paper from 2021, this also has 5 out of the 9 pairs can be reduced. So we can find explanations that are smaller than the pairs. Talk about formal explainability. Again, as I said, we have an instance and a pointing feature space and a class. And we have 2 types of explanations. An adaptive explanation answers the why question. So for us, an adaptive explanation is a subset minimal set of features that is sufficient for ensuring the prediction. So essentially, we can state this as a first order logic expression for all pointing feature space. If the feature is one of the selected features and it keeps the value, if all of the features in this set keep the value, then the prediction is going to be the one we intend. A different type of explanation is a contrastive explanation. So which answers the why not explanation. So in this case, it's a subset minimal set of features that is sufficient to allow the prediction to change. So how do we state this? So there exists a pointing feature space such that if all the features that I'm not allowing to change keep the value, but the other ones are allowed to change, then I will find a point where I can change the prediction. And so since we want to set minimal features, we can formulate this as it's a set such that the predicate holds, and for any subset, the predicate does not hold. So the predicates are these 2 here. So we call this a weak AXP, weak CXP, and essentially we want to find the set minimal set such that these predicates are true. We prove, actually we have 2 results on duality, and the previous talk talked about duality. So we most recently, last year, we proved that the adaptive explanations are minimal hitting sets of contrastive explanations and vice versa. And the previous year, we showed that there was a tight relationship between adaptive explanations and adversarial examples. So this was a paper that we published at NIBS. So this essentially addresses some of the questions in the previous talk as well. What is interesting in some of these results essentially that we have a rigorous way to relate why and why not explanations using minimal hitting set duality. And we have a few more results. Essentially, the idea of minimal hitting set duality is not ours. It can be traced to the 80s, but the application in explanations in artificial intelligence is our most recent work. Okay, and so we can have a few more additional results. So the conditions for adaptive and contrastive explanation are monotone with respect to set inclusion. So that this means we don't have to test of a subset. We just need to remove an element at a time and check if the predicate still holds or not. So essentially, this allows us to have a very clear approach to do explanation. So we could classify it in a suitable logical representation, and then we can compute adaptive explanations or contrastive explanations by iteratively dropping features and checking whether the predicate that I showed in the previous slide holds. And we pick a reasoner according to the logic we used to encode the classifiers. So this essentially summarizes the algorithm. It's simple. Of course, we are hiding the complexity by having an encoding with a suitable logic representation. The question now is, how do we do this in practice? So how do we do this encoding? And so let me briefly describe an encoding using of neural networks. So this is a very simplistic neural network. We are, for simplicity again, we use ReLU as the activation function. And what we assume is that we have blocks, with the exception of the first layer. Everything is a block. Each layer is a block, and we compute an intermediate value x prime starting from the input x using the weight matrix, and then and also some bias vector. And after we have this intermediate value, we compute the output starting from the intermediate value and using the activation function, in this case ReLU. So essentially, what I said in the previous slide is that I compute this intermediate value using the weight matrices and the bias vector from the inputs, and then I rectify using the intermediate value and 0. So I pick the max. So this we can represent with a mixed integer linear programming or satisfiability model theories. And so it's basically well known. It's been around for a few years. So the summations that we have up there, we represent, we equal them to the difference between two non-negative variables, and we use a Boolean variable to allow only one of them not to be 0. So since they are non-negative, and here we are imposing them to be not positive, essentially only one of them can be positive. And so the idea is that if this summation is positive, the value is put in yi, it's the only solution. Otherwise, if the value is negative, yi is 0, and the value is put on the select variable si, which is positive, and so because it's minus si, it becomes negative, of course. And so this is a very simple example just to show that this is not difficult to do. So we have a very simple neural network, a summation, a ReLU activation function, the inputs. And so we can, for this very simple example, write down by ourselves the logic encoding. And then we can, for different types of values, plug in the values and see what we are getting. So essentially, of course, in practice, this is done automatically. This is just to show that it can be, even for a small example, can be done by hand. And so these are some initial results that we got 2 years ago for using the neural network. So when I say minimal, it's subset minimal explanations. Minimum are cardinality minimal explanations. These are different data sets, number of features, smallest explanation, average size of explanation, or largest explanation. And these are the sizes, the runtimes using an off-the-shelf SMT solver or an off-the-shelf mixed integer linear programming solver. And for neural networks, this is an NP-hard problem. For smallest explanation, it's in the second level of the polynomial the decision problem, and so that's why in some cases you cannot even compute the explanation. What we observed first, this was the first rigorous approach for explaining neural networks. The downside is that it scales to a few neurons. And more things. So we can. I'm going to those are the bad news. We have some good news. So for example, for decision trees, we can do explanations in polynomial time. So I'm just going to briefly show make the claim. So it's the algorithm is very simple. We can essentially, if the prediction is plus, we just have to make sure that the paths to minus are blocked, and we can find that in polynomial time. It's a well-known result. And these are some results just to show that even for decision trees, we need explanation. So these are the number of, I showed before, you can have a significant number of redundant pairs in those decision trees. And if the pairs are redundant, the percentage of filters that we can drop can be significant. And these are two different tools. This is a commercial tool. This is a well-known tool for learning decision trees. This summarizes the progress that we have witnessed in formal explainability. So we have a bunch of results. So polynomial time explainability for different types of classifiers, naive Bayes classifiers, decision trees, monotonic classifiers, and so on. For some others, we have proved that they are hard in theory, but in practice they are very efficient. The decision lists, random forest, and boosted trees. And we have two challenges still, which are neural networks and Bayesian networks, which are not only computationally hard, but in practice they're also hard to solve. So just to show that in practice we can get pretty good results, this is for random forest. So these are the we have a lot of data, but I'm just going to show the run times. So this is the average run time that we got for different types of data sets. And this is a tool, a model agnostic heuristic tool. So again, no quality in the explanation. As you can see, we are usually an order of magnitude faster than Anchor for finding a logically rigorous explanation. Okay, so the talk, I talked about very important misconceptions in widely used XAI approaches, both model agnostic and intrinsic explainable approaches. I introduced formal explainability in AI. So it's logic-based, it's rigorous definitions of explanations. We can answer why and why not questions. And we show that there is important duality relationship between these two types of explanations. And I did not have time, but we have also other problems of crucial importance, like enumerating explanations or deciding membership of features in explanations. And we have come across some recurring misconceptions about the limitations of formal AI. So the first is that logic is not expressive enough for machine learning. So this is, at least in our, until now, we could not find any machine learning model that we could not encode in logic and reason about it. And another misconception is polyability. So this is, as I showed in the last part of the talk, it's not an issue for many classes of classifiers, so decision trees, naive Bayes classifiers, monotonic, but also decision lists, random forest, and boosted trees. It is still an issue for neural networks and Bayesian networks, and that is a challenge for the near future. So I will be happy to answer your questions. Thank you.
Thank you, João, for this very nice talk. Yes, do we have questions in the audience? Let me see.
I have a question.
Please. Bonjour, Marie-Christine.
Bonjour.
Bonjour, Marie.
I have a question about you say that for now the scalability is an issue for a neural network. Do you have any idea to how to address this problem?
Well, there are two ideas. So one is not ours actually. It's a group in the north of France. They propose to approximate neural networks with random forest and then expand the random forest. And for that, as I showed in my talk, we can get very good results with random forest. So that would be an indirect way to solve the problem. A second way is to pursue the work that has been done in robustness, where we have to develop specific reasoners for neural networks, and there have been some good results from Stanford, at least one group in Stanford, where they have been improving the performance of reasoning about neural networks, and we can tap on those results. So I would expect that we can continue to see improvements in the ability to reason about neural networks. If you ask my honest opinion, we can do a few tens of neurons. They can do a few hundreds of neurons. People want lots of thousands of neurons. So we have a lot of work to do in that area still. So I think for now, approximating neural networks with some other model is probably the best solution.
Okay, thank you.
Yeah, I have a follow-up.
Please,
Yeah,
madam.
I mean, that's kind of my question too. Was, I guess when you say approximation, there's a lot of abstraction refinement kind of work where they merge nodes and then refine on a new basis. There's a person called Guy Katz and a company. Anyway, so that is probably what you meant when you said approximation.
No, yeah, thank you for the question. Let me, I'm sorry for interrupting, but no. What I was essentially think of a tool like Lime or even Sharp, where you can, the explanation is that in the case of Lime or Sharp, it's usually a linear classifier, but you can run a decision tree. What we are saying is that you can use a similar approach to run a decision tree or a random forest, and then use logical-based methods to explain the explanation itself. So because what we argue is that those explanations are really, first, they are, number one, they can be incorrect, but essentially, even if they are correct, they bring with them information that you don't need, as I showed also in my talk. And so what we are saying is that you can train a classifier that behaves almost as good as a neural network, close to the instance that you are interested in, and then you can explain with rigorous methods. So because, as I said, even if you have a decision tree or if you have a random forest, the information that you are getting requires explanation.
Okay, so and then I'll pose my question in a slightly different way. Okay, so so there have been a lot of work in formally proving robustness and various properties about neural networks. Okay, for very large systems using SMT solvers and SAT solvers. Okay. Now, they may not be doing explanations, and there the scalability is addressed in two ways. One is by developing special purpose decision procedures, okay? So like ReLU-Plex and so on. So, and that is one. The other kind of work is using abstractions of neural networks, okay? So my question then would be, if those kinds of abstraction techniques that have been used for the other ones can also be considered for doing the explanation kind of analysis, the kind that you're doing.
Okay, thank you very much for the question and for the clarification. Yes, so in my answer to Marie-Christine, I mentioned the Stanford group. That's the group that developed ReLU-Plex, and so we can tap on those results. There are also groups doing what you mentioned, abstraction-based methods. We can also tap on those. Yes, I'm not familiar with any work that has done that. It's a very interesting perspective as well. Again, because with those abstraction-based methods, you make also compromise in terms of the accuracy, and so you need to check, and then you might need to refine your abstraction.
That's true. We have been doing some work in that area, so I'd be interested in.
That we think we could certainly tap on that for explainability.
Thank you.
Again, I'm not familiar with any line of work there, but yes, it's certainly a possibility. Thank you very much for the question. Yes.
Okay. Any other questions? Okay. Then the organizers have asked us to all turn on our cameras again to take one more group photo. So if you're all willing to do that, that would be great. Don't forget to smile, Katie. Is that good?
He's still taking it.
Oh, he's still taking it.
It's done. Thank you very much, everyone.
Thank you, Paresh. Okay, so we now go to Marie-Christine Rousset's talk. So Marie-Christine Rousset is a professor of computer science at the University of Grenoble, Alpes in France, in Grenoble. And she's worked a lot on knowledge representation, information integration. But she's recently gotten very excited, very interested in explainability, and she's the coordinator actually of the European Taylor project on foundation of trustworthy AI integrating learning optimization and reasoning. And she's also a chair in the Grenoble 3AI Institute called MIAI, where she's responsible for the chair for Explainable and Responsible AI. So Marie-Christine, you
yes.
have the floor. I
Yeah.
guess you can take the charge of the screen.
Yes, I will try to do it. Yes.
And your title is a query-based approach for analyzing and explaining privacy risks. So it's great to have you here. Thank you.
Okay. Can you see my screen?
Yes. Yes.
Okay. So thank you very much for the opportunity to speak about this work. So it is related to explanation, but mainly also on the privacy aspect. That, as you told, we are studying in the share that I'm co-leading with one of my colleagues about explainable and responsible AI. So we have also aspect on privacy and fairness. So this work is a joint work with colleagues, and Ira is a PhD student that is funded on the MIAI Institute budget. So the general setting of our work is to handle privacy risks that are raised nowadays by data sharing through smart devices that are connected to service providers. So a lot of personal data are at the moment disseminated over internet through mobile devices or smart environment that you can have at home. And so there are a lot of privacy breaches in different aspects in the network, but also in the fact that at the moment, the model that is implemented is that the data producer transmit all their data to a centralized service provider who consume the data to do some data analytics or and things like that. So our vision is to change this centralized view and to rely on as much as possible data decentralization and encryption for data exchange through the network. So it is a way for limiting the privacy breach to give the control somehow to each data producer on his or her own data, and to keep the control to accept or not to transmit data to a centralized service provider. That cannot be avoided, of course, because there are many useful things to do it in a centralized manner, in particular to do some data analytics that can be useful for the data producer. So our vision is the following: the data producers should keep the control of the data they accept transmit to a data consumer in exchange of services. And so in this way, the data centralized by the data consumer, who is also the data provider, the service provider, sorry, are not considered as sensitive data by their owners according to some privacy policies. So each data producer should be able to express his or her own privacy policies. And the data consumer has to explain the service for which he requests the data according to his or her utility policy. So all of this is also, of course, a question of finding a trade-off between privacy policies of data owners and utility policies of service providers. So our proposal is based on using queries. In fact, in our view, so queries are very standard in database, but it is also can be seen as logical formulas over a schema or an ontology of a domain. So we will use this formal approach for the specification and the verification of privacy and utility policies. and we want to do it as a level of the queries, and so independently of the data. And an important point is that we really, for privacy purposes, we really have to consider aggregate queries over temporal data, because more and more we are aware that temporal data, for instance, your consumption, the consumption of electrical consumption over time can be very sensitive. You can guess many things by simply analyzing precise temporal series about people. And we also use this query-based approach for the design of a negotiation mechanism that can be triggered when the utility policies turns out to be incompatible with the privacy policy. And so for this negotiation mechanism, we plan to use query relaxation techniques to propose new utility or new privacy queries in order to find a trade-off that is acceptable by both the two sides, the data producer and the data consumer. So just I will try not to be too technical, but so we consider in this setting quite complex queries that are required, as I told, because we have to consider aggregate queries about temporal data. And this, okay, so there are this queries is just an abstract syntaxes that I will not go into the detail. And these temporal aggregated conjunctive queries are evaluated over local temporal knowledge graphs that are time-stamped facts, time-stamped triples. And this can be implemented using a recent extension of RDF and Sparkle that are the standard for modeling and querying knowledge graphs. But here they have been extended recently to take into account temporal data and temporal queries. So in terms of queries, what does that mean? That utility policy, so utility policy and privacy policies are expressed respectively as sets of queries, temporal aggregated queries. And a utility policy will be said as satisfied by a data producer if this data producer accepts to transmit to the data consumer the answers of the utility queries that are that the data consumer wants to get the answers. So here is an example. It can be, for instance, the data consumer to offer a service to his client can be interested in asking, for instance, the average consumption computed every hour over the previous hour. It is the time window usefulness, and grouped by consumers, street, and time window end of data producer living in Grenoble whose family size is greater than 2. So here is the translation in the abstract syntax of the utility query, and this utility query is kind of explanation, justification of the request of the data consumer, and it can say, if you accept to give me this information, if as a data producer you accept to answer to this utility query, in return I can give you the average consumption of home that are similar to you, with similar family size and similar urban setting. So a privacy policy. So first, an important point to say that the privacy policy is kept secret by each data producer, and it will be satisfied when no answer of any of these privacy query is disclosed to the data consumer. So it kind of unsat queries. So you express by queries what you want to keep, not to divulgate. So here, for instance, a very simple privacy query is to forbid the disclosure of the street and the city of the consumer. So it can be in this way, the privacy query say what explicitly here as a query, what he wants to keep, to control and not to transmit. So first problem to study when the privacy and utility policies are specified in this way. So I explicitly specified it to check if they are compatible. First thing, and so the intuition there is a formal definition, but the intuition is that the utility policy will be incompatible with the privacy policy if it is possible to infer, logically infer answers to a privacy query based on answers to utility queries. So to be formally defined, we have to, the definition is based on what we have called the logical signature of an answer of a query. A logical signature of an answer of a query, it's simply the logical specification of all the data sets that what is common in all the data sets that provide, that support this answer. So for instance, if I consider this privacy query, which is quite simple, it asks for the data producer identifier, the street and the city of the, and so if there is an answer, for instance, this one, DP1, Alsace-Lorraine and Grenoble, based on the query expression and based on the specific answer, here is the logical signature of this answer. It just say that this answer just say that in the data, even if I don't know the data, I know that in the data there exists an A such that DP address A and A is as a value Alsace-Lorraine for street and A as a value Grenoble for city. So it is just based on the answer that can be divulgated or not and the query expression. So it is the notion of logical signature is quite is complicated by the fact that our queries are quite complex. So we have to extend it to take into account the aggregation and the possible filter condition, but I will not go into the detail. It is just a more complex logical formula. But the point is that this complex logical formula can be decomposed in 3 parts that can be considered independently for the rest of for the reasoning problem, in fact. Oops, sorry. Okay, what happens? Okay. So we have studied this incompatibility problem, and so we have first obtained a characterization of incompatibility for simple queries without aggregates. And so the theorem says that there is an incompatibility. So first, we have to consider each privacy query compared to the set, possibly the set, the union of all the utility query. And here we extend a standard technique which have been used for checking, for instance, query inclusion, query containment, which is freezing the body of a query. So I will just explain it on an example. So here, suppose that I have this privacy query. Okay, that say that we don't want to reveal for a given X its street. And you have two utility queries. One asks for the city of a consumer, and the other one of a street of a consumer. So the approach is we take the union of all the bodies of the utility query, and we replace the variables by constants, and we obtain. So here, for instance, a way to freeze the variable of the first one is to replace them by constants C1 and C2. And we do the same for the body of the second utility query. And notice that the freezing in our setting, there are not a single freezing, but different possible freezing that may replace distinct variables of the utility queries with same constant if these variables are output variables. So it's a little bit technique, but here in my freezing here that I show, I replace this variable of the utility query x2 by the same constant for freezing the one of the variable of the utility query. And it is a way to simulate the fact that when you have answers to utility queries, you have instantiation of their output variables, and this instantiation can occur in a way that make possible to provide a non-empty answer for the privacy query, which is a case of incompatibility. So the point is that we detect the incompatibility, but we can also provide, based on this technique, an explanation to the data producer. So it could be like this. It is I give it in the in natural language, but it is not done as natural language, but it can turn out in natural language, saying that if you accept, so it is an explanation to the data producer to say, be careful, these utility queries don't answer to them, because if you accept to answer to these two utility queries, there is a risk that there are two answers where with a join possible with a constant that are among these answers. And from these two answers, and based on the query expression that the data provider has, it can guess, it will infer that C1, C4 here is an example, is an answer to your privacy query, so violates your privacy policy. Okay, so then I will not go into more details, but we have extended this characterization with, in the case of aggregate, but with same time windows. So in the presence of aggregate function in privacy query, first point is that utility queries have to be checked one by one, so you don't have to consider their union. And we have this full characterization when no filter condition and the aggregation function is the same. Finally, in this setting, for incompatibility, we have to, through possible freezing of constants of each body of the privacy query and each body of the utility queries, we can make them isomorphic. So it is a strong, characterization. In the other case, it's not incompatible. Okay, so it is an ongoing work, since it is done in the PhD thesis, which is at half in the middle of the duration. So the first the ongoing work which is ongoing, it is the implementation of the theorems that we have that I have just mentioned previously, and of other sufficient condition of compatibility. that are more efficient, but are only sufficient. And the most important remaining work is the design and implementation of a negotiation mechanism in case of incompatibility. Okay, so thank you. I am ready to answer questions if you have.
Thank you very much, Marie-Christine, for this talk. Yes, are there questions from the audience?
So how do you, yeah, so I have a question. How do you, how are these utility queries, and so they are provided to you upfront? Are they given to you and you work with them, or so
yeah.
when
Yes, in fact, in this I have presented the formal framework, which is based on these queries expression, which are kind of logical expression of things that have to be, yes, that of course we are not going to ask real end users to express these queries, of course, but there is something that we have to give the means to data producer to be sensibilized to this problem and to help them to express their privacy policies. So to express what they want to keep secret, and of course to help them to express it, specify it formally as queries. Of course,
you would have to provide them with that whatever language that they need.
Yeah, yes, of course, of course. Mm-hmm.
Okay.
Other questions? I'm looking at the chat. Excuse me, Marie-Christine. Okay, I don't see. I'd like to ask a question, Marie-Christine. Well, actually, two. So the first is, the kind of explanations that you're giving here they're particular kind, right? So it's about a particular setup where you have certain information that you want to keep private, and another person wants to get that information, and you're explaining risks of violation of privacy through this logical mechanism. So to that extent, it seems to me like a rather special notion of
Yes.
explanation. How do you see it generalizing to the more general kinds of cases of where we've been talking about in Vinesh's talk and in Joao's talk about just basically trying to understand, interpret the behavior of machine learning systems, whether it's a kind of image recognition system or something that's work on data?
Okay, so it is yes, it is hardly generalizable for all the setting. I would say that if I want to, I would say that we are in the setting somehow where the models here of privacy and utility are transparent, interpretable, since they are made of logical specification or queries that are the same. Okay,
right.
So but that for a user it is difficult to tell them, look at this formula, and in some cases that can be a problem. So it is a way, by this freezing, to make them to make it more concrete, but it is a way to transmit to them that some part of the model that in a more concrete way than just give the formulas.
Okay, so yeah, that's interesting. So it seems to me then that what you're isolating here is an important aspect of interpretability. It goes back, I think, to Mandayam's original question that we haven't really yet looked at. There's an important pragmatic component to explainability. So, and what you're noticing, what you're showing us is that even when we have proofs, these proofs may not be things that are understandable by the user, or even maybe they may not be relevant because it might not be the right kind of thing that they want looked at. And so that leads me to just think about my second question, if I may, which is, you're talking about resolving incompatibilities, and that's again where this pragmatic notion might rear its head. So you have, can you tell us a little bit about how you're thinking about resolving the incompatibility between the privacy and utility policies.
Yes. So our idea is to since we have the policies are expressed as complex queries with several parts, there is a way, in particular, we want to play. It seems to me the more useful and relevant way to do it in this setting. It is to play on the size of the time window. You see, you can, for instance, you can not accept to provide your consumption every minute, but you can accept to do it every day. To give the consumption, the average consumption computed on every day instead of computed on every minute, because it will reveal less things about your private life. But if you do that to protect your your privacy, if you do that, maybe the data provider will say, but I'm sorry, but if you give me the average of your electrical consumption only computed on every day, I will not be able to do interesting analysis. So can you? So do you agree to, let's say, to give me every hour? And you see, and then you can play on this, and each time, of course, to verify the compatibility of this of this new relaxed queries.
Right. Okay. Yes. Okay. Thank you. I see that. Great. Okay. I guess we are. Oh, we're actually doing relatively well. Amazing. So thank you so much, Marie-Christine, for your talk. We will now pass to.
Yes, I stop. Okay.
Sorry. To Amit Deshpande's talk, which is on. Now we're going to look at. We're going to look at fairness. We're going to come to the issue. We're sort of gradually going through. We've seen some issues about fairness, or in some sense, in Marie-Christine's talk, and now we're going to get a talk on fairness and robustness in responsible AI from Amit. Amit is a researcher at Microsoft Research. He's published on quite technical issues of in machine learning, but we're looking forward to listening to your talk. I have a funny message here, but I hope this is okay. Amit, are you there?
Yes. Just a minute. Let me share my screen.
I was just asked if you to start a video, so I hope that's.
Okay, good. Okay.
Yeah.
Okay. You have Halloween decorations.
Okay, sorry. Then let me just check. Is this? Okay. My daughter did this. Sorry.
It's great.
No, she did this for her class. Oh.
Yeah.
Okay. Just a minute. Could you see my slides? Okay. Can you see my slides?
They're coming. Yep, they've come up. Yep, great.
Okay, good. Okay. So I will be talking about fairness and robustness in responsible AI. Thank you for the introduction, Nicholas. Okay, let me just check it. Okay. So here is the outline. Basically, we'll start. So I will tell you a little bit about responsible AI, then the kind of principles or metrics that are used in responsible AI, the axes of responsible AI in some sense. I will tell a little bit about fairness metrics and bias mitigation, and similarly robustness metrics and building robust models, because fairness and robustness, these two are two of the important axes of responsible AI. And then I will tell you a little bit about some of the recent results that I have with my co-authors on trade-offs for different metrics of fairness and robustness. And in a sense, they also pose some questions about the challenges that we see ahead for responsible AI, testing of responsible AI systems, and deploying responsible AI models and systems. So the bias or the harms of AI models and systems, they have been in spotlight for many years now, or at least they have, in the last few years, they have been highlighted many times. And there are things like, there is this EU AI Act proposal. So there are regulations that are coming up to regulate AI models and systems. And similar to the way EU, the European Union GDPR Act sort of affected the way people look at privacy, this AI Act proposal is going to also change the way we think about responsible AI systems, how we test them, how we deploy them, etc. So privacy comes foremost, because that's where for any AI model or system, you collect data, and because of that, privacy comes first, and that's what we saw in GDPR. But fairness, robustness, transparency, interpretability of AI models and systems, these are going to be important topics going forward. These AI models and systems, they have intended as well as sometimes unintended harms. The problem is that many of these are complex black box systems. So they are not, even the people who build them don't completely understand them. There is also sometimes there are these terms called as disparate treatment and disparate impact, where disparate treatment means there is sort of intentional discrimination, which at times may be justifiable. Whereas there are laws which talk about certain outcomes where in terms of employment or housing, there are laws in the US, and the EU AI Act, the proposed EU AI Act is also going to talk, it also talks about some of these outcome-based notions of harms, which come under the term called as disparate impact. So sometimes you do not want certain outcome-based metrics to be discriminatory when you measure the system or its outcomes on sensitive groups such as different races or genders. Then the thing is, sometimes what happens is these AI models or systems, they have unknown failure modes post-deployment, and it's very hard to correct them later. So because of that, it's important to test these systems, also come up with mitigation strategies to minimize the harms or to mitigate the harms. So there are these violations of responsible AI standards, which comes to measuring them. So to measure them, we need to quantify laws, regulations, and ethics into metrics, which is sort of, I will not talk about many of these things, like how to convert laws into regulations or ethics into quantifiable metrics, but people have done this in the past in the context of employment or housing. And also people are trying to do this for, say, in the context of, say, AI in credit scores or lending and mitigation algorithms. So in this talk, I will give you a glimpse into what kind of questions arise in the context of fairness in responsible AI and robustness in responsible AI. So in case of fairness, classification and ranking are two important problems that machine learning or AI models try to solve. And in group fair classification or group fair ranking, where groups means sensitive demographic groups, these could be races or genders, and outcome-based fairness. So there are different notions of fairness. One would be outcome-based fairness. So for example, in classification, we want equal false positive rates on two groups or across groups, or equal accuracy across groups. There are also representation-based fairness metrics that are developed based on the classification, group fairness in classification, and applying it to ranking, where we would want, say, demographic parity or equal representation in the top K, or some sort of minimum representation guarantee for each of the sensitive groups. So there are, one question is, typically, if we measure the fairness as only outcome based, then is it at odds with individual fairness? So for example, a random classifier is group fair. That is, it would have equal false positive rates or equal accuracy across groups. But it is individually unfair in the sense that it treats high risk and low risk individuals similarly, or it does not treat, for example, two individuals who have similar risks or risk profile. It treats them arbitrarily because it's random. So even though the outcome may be fair, it may not be individually fair. Also, in case of ranking, if we think of group fairness, so typically group fair re-ranking algorithms, what they do is they maximize some aggregate ranking utility while maintaining certain minimum representation guarantees for groups in the top ranks or sometimes top prefixes. Now the thing is, the question is, many times if we have these bias mitigation strategies, and if they are perceived to be anti-meritocratic or not satisfying individual fairness, then there is a problem. As in, it would be hard to convince people that this is still good. And the other question is, can we, if these are at odds, can we somehow balance these? Because many of the complaints about unfairness that come for these AI models or systems post-deployment, they are about individual fairness, saying that two similar individuals, they were treated differently or not in a similar fashion by these models or systems. So one question about group fair ranking is it anti-meritocratic in some sense? Or does it underrank individuals from one group to achieve group fairness? So as I said, let's look at fairness in classification first. So in fairness in classification, there are these outcome-based notions of group fairness. There are also notions of individual fairness. So there is a definition by Dwork et al., which says that the prediction should be similar for individuals with similar features. And as we saw, the classification, a random classifier is group fair, but individually unfair. And there is a known group fairness versus accuracy trade-off, where you can also exhibit this. So here is an example from synthetic data set where you have an accuracy maximizing classifier. So here the group-wise, class-wise, it's a synthetic data where there are two groups and it's just binary classification problem. And the group-wise, class-wise distributions are just Gaussians. And the accuracy maximizing classifier here on the left is not group fair. But on the right, you see a classifier that optimizes accuracy, that maximizes accuracy under group fairness constraints. And here it achieves a low accuracy of around 0.5. This is like an example, an extreme example where group fair classifier, or the optimal group fair classifier, actually behaves like a random classifier. It has a very low accuracy. So typically, group fair, the mitigation algorithms, the bias mitigation algorithms, or group fair classifiers, what they want to do is they want to maximize accuracy subject to some fairness constraints. And the fairness constraints may be not perfect group fairness, that is may not be equal false positive rates on two groups, or may not be equal accuracy on two groups, but near equal accuracy, where this nearness can be quantified by some parameter. saying that we want the group-wise accuracies or group-wise FPRs to be within some lambda factor of each other, and subject to that constraint, we want to maximize the overall accuracy. So in a joint work with Arpita Biswas, Siddharth Barman, and Amit Sharma, what we did was we looked at a different definition of individual fairness. So even though we don't call it individual fairness, it's called inframarginality. And unlike the previous notions of individual fairness, where individual fairness was defined as having similar outcome or similar prediction for individuals with similar features, here we look at inframarginality as a quantification of how much a classifier deviates from a threshold classifier on the true risk probability of individuals. Where true risk probability is, so if you think of your data as x comma y comma z as a joint distribution, where x denotes the features, y is the true label, and z is the group membership. Typically, like if you ignore the group fairness part of it, we just look at x comma y. And the base classifier that maximizes accuracy is basically it puts a threshold of half on the probability of y equals 1 conditioned on x equals little x. So conditioned on the features, what is the probability of the true label being 1? If we put a threshold of half, we get the theoretically optimal classifier, which is, like, by optimal we mean the classifier of maximum accuracy. That's the base classifier. And it's a threshold classifier, and it has zero inframarginality with respect to the threshold of half. Whereas now with this definition, if you look at random classifier, then random classifier has high inframarginality with respect to any threshold, because random classifier is far away from any threshold classifier on the true risk probability of individuals. So what we did was that we looked at this as inframarginality with respect to a threshold as our notion of individual fairness, but let's call it inframarginality for now. So it turns out that one can also relax this notion, where it's okay to sort of to treat individuals differently when they are very close to the threshold, but we don't want to treat individuals differently if their true risk probability is far away from the threshold. So this threshold is sort of a threshold which tells you that if the true risk probability is more than this threshold, then that person is high risk. If it is lower, then it's low risk. And we don't really want to confuse between individuals who are actually high risk and away from the threshold versus the individuals who are low risk and again away from the threshold on the lower side. So it turns out that so we did inframarginality audit of some group fair classifiers, some state-of-the-art group fair classifiers, and what we found out was that some of these group fair classifiers can have very high inframarginality. So here is an example. There is this classifier called as metafair classifier, which is part of many of these fairness toolkits. For example, AIF 360, which is an open source fairness toolkit by IBM. So inframarginality audit for metafair classifier. So you can see in this plot, there are these different values of lambda, and higher lambda means more group fairness. So for metafair classifier, as lambda increases, it gives you more and more group fairness. So for example, if we want, say, equal FPRs, higher lambda means that you would get near equal. So when lambda becomes 1, you are maximizing accuracy subject to equal FPRs on two groups. So it turns out that as this lambda parameter increases, the inframarginality becomes high. And it can be, in fact, the black line here denotes the random classifier, the inframarginality of a random classifier. And it can be almost as high as that of a random classifier. So we don't want this to happen, that we have a group fair classifier, but it treats individuals very differently, who have the same true risk probability. Now you may ask that typically, like, how do we get the true risk probability? So the thing is, we show theoretically that under some reasonable assumptions, even if you don't have the true risk probabilities, but have good estimates of them, and if we compute the inframarginality, if we do this inframarginality audit with these estimates of the true risk probabilities, still the inframarginality value that we compute would be not very far from the inframarginality value computed using the actual true risk probabilities. So it's sort of worrisome that some of the group fair classifiers can be as bad as random classifiers in the context of inframarginality. Secondly, you can also use inframarginality in a positive way, that suppose you have a choice of different group fair classifiers and you want to test them for individual fairness or inframarginality, you can actually compare them and see if they are similar, if they give somewhat similar group fairness, do they give very different individual fairness, and in which case it also gives a metric to compare them and pick the classifier that has low inframarginality. So we looked at some of the group fair classifiers. Here are some of them, like metafair, ROC, reweighing, and adversarial debiasing. So some of these methods are in processing, some of them are pre-processing, some of these are called as post-processing. So that's how the group fair classifiers are divided into which part of the training, which part of the model do they change to make it fair. So some of them require like training the model from scratch. Some of them require just post-processing. They don't change too much of the training part. They only change the final outcome in some way. So here, for example, it gives, one can do an audit based on inframarginality and pick the best classifier among multiple group fair classifiers. So that was the key, that was the key takeaway for us from this inframarginality audit of group fair classifiers. Now let me move to fairness in ranking. So in group fair ranking also a similar problem arises, that typically the notions of fairness are representation-based fairness, which means equal representation of groups in top K or prefixes. There is also a similar, there is a notion of individual fairness also used in learning to rank literature, which looks at similar exposure for items with similar features. And in group fairness, if it is representation based, it may happen that it satisfies representation based fairness, but it puts individuals from one group in the bottom half and the individuals from other group mostly in the top half, which might still be not fair. Like it might satisfy some notion of equal representation, but it may not be fair. Well, prefix can still solve it, but there are also further questions about whether it is anti-meritocratic. So the group fair ranking work can be divided into two parts. One is like group fair learning to rank, where it takes as an input data of say pairwise comparisons, or so it has some training data, whereas group fair re-ranking, it takes just a ranked list and it does re-ranking to satisfy group fairness. So the ranked list, people look at also questions where for every item, either there is an important score or for every item and position pair, we know the ranking utility of putting that ith item in jth place. And group fair re-ranking algorithms, they maximize aggregate ranking utility while maintaining some minimum representation guarantee for groups in top ranks or top prefixes. So we'll ask this question of whether group fair re-ranking, does it lead to under-ranking of individuals. So for example, here there is a re-ranking of the top 6 positions. It gives fairness in, say, the prefixes which are, it gives group fairness in prefixes, but there is one individual who gets ranked lower than his true rank. So we looked at this problem of under-ranking and group fair ranking. And we define under-ranking as the worst case multiplicative displacement of an individual's true rank after a group fair re-ranking. So here again, the caveat that you need to know the true rank. But suppose there is a way for us to know the true rank, because there are also questions of implicit bias, because of which we may not really know the true rank of an individual or an item. So we study this trade-off between group fairness and under-ranking. I won't go into the details of the technical details of lower bounds and upper bounds that we show. So we show lower bounds on the optimal trade-off between group fairness and under-ranking, and we show an efficient re-ranking algorithm which simultaneously gives under-ranking guarantees as well as group fairness guarantees. And this was joint work with Shruti Gorantla and Anand Lewis from the Indian Institute of Science, and it appeared at ICML this year. So what a couple of important things about this is that the group fairness versus under-ranking trade-off is like group fairness versus the worst case individual fairness trade-off, and under-ranking is different from ranking utility. Like in some cases, you may think of ranking utility also as a measure of individual fairness, but it's a measure of aggregate individual fairness, not worst case individual fairness. So the trade-offs between, say, group fairness and ranking utility don't really imply trade-offs between group fairness and under-ranking. And the algorithm has, our algorithm has basically 2 steps. What it does is it creates some positions, unfilled positions. So it moves down individuals to bound the under-ranking and satisfy the upper bound group fairness constraints, and then moves them up again to satisfy the lower bound group fairness constraints while preserving under-ranking and the upper bound constraints. So I won't go into the details of this, but the experiments that we did, experimentally what we could show was that our algorithm is much faster than the state-of-the-art re-ranking algorithms. And at the same time, it gives the best of representation-based fairness or group fairness and individual fairness, which is measured as under-ranking. So now let me change the topic a little bit and talk about robustness and classification. So in fairness, we saw this trade-off between, say, group fairness and individual fairness in classification and ranking. Now let me tell you about a trade-off between 2 notions of robustness in classification. So it's known that these neural network models, even though they have high accuracy, they are brittle in the sense that they are not robust to adversarial perturbations. For example, a highly accurate model can be fooled by adding a small pixel-wise perturbation to it, which is imperceptible to the human eye. So robustness in classification has mostly focused on adversarial robustness, which means robustness to small pixel-wise perturbations that are imperceptible to humans. But in a recent work, what we looked at was also spatial robustness. Spatial robustness has been studied in the context of machine learning models and neural networks for a long time, but it has been it has been about robustness to geometric transformations, like for example, translations, rotations, and scaling. So these are perturbations that humans can perceive and correct for. And to build spatial robustness in models, so the typical methods that are used to get adversarially robust models and spatially robust models, they are very different. So I will talk about these. This is joint work with Sandesh Kamath, KV Subramaniam, and Vineet Balasubramaniam, and it's going to appear at NeurIPS. The interesting part is that the methods to build robust models for adversarial robustness and spatial robustness, they are very different. So traditionally, what has been done is that for adversarially robust models, we do adversarial training. That is, we train with adversarially perturbed training data while keeping the labels unchanged. Whereas for spatially robust models, we use equivariant, so group equivariant neural networks, which are generalization of standard CNNs. Like standard CNNs are equivariant to translations. In the last few years, people have generalized these to group equivariant neural networks, which are equivariant to groups of rotations or other transformation groups. And even though these models are equivariant, to make them invariant to spatial transformations, we still need training augmentation with larger and larger transformations. So what we observed was that spatially robust models trained with progressively larger spatial transformations. So here on the left, you see a figure where these are models trained with these different colors. They denote models trained with larger and larger equivariant models that are trained with larger and larger rotation ranges. Ranges which are, so for example, the line 120 would denote a model that has been trained with rotations in the range of -120 degrees to +120 degrees. And this rate of invariance is basically, it captures how invariant it is to a rotation range which is given on the x-axis. And we see that as the models are trained with progressively larger spatial transformations, their spatial robustness increases. But on the other hand, their adversarial robustness progressively decreases. And on the other hand, if we do adversarial training, so if we take a model and do adversarial training with progressively larger pixel-wise perturbations, then that improves the adversarial robustness, but it progressively decreases the spatial robustness. So there is this trade-off between adversarial robustness and spatial robustness, that the traditional methods that we use for adversarial robustness, they decrease the spatial robustness and vice versa. So how can we balance adversarial and spatial robustness? So we propose a training method based on curriculum learning that trains with progressively more difficult input perturbations. So it gradually introduces more difficult input perturbations, which is larger adversarial perturbations as well as larger spatial transformations. And by doing that, we get models that have good adversarial as well as spatial robustness, as opposed to only improving one of them at the cost of the other. So I will stop here. These are just some illustrative examples that I wanted to give from recent work where one has to look at some of these aspects of fairness and robustness, where we want the models to be fair, but with respect to group fairness, individual fairness, or both. And similarly, in case of robustness, we want robust models that should be robust to adversarial perturbations as well as, say, natural perturbations, which are spatial transformations. And achieving that has some of these interesting theoretical as well as like empirical study. So some questions that are important to explore from theoretical perspective as well as empirical perspective. And to summarize what EU GDPR, the European Union GDPR did for data privacy, the EU AI Act proposal will do for responsible AI. And classification, ranking, recommendation are some of the important applications with societal and economic impact. And testing fairness, robustness, transparency of AI systems and building responsible AI models, this is going to be an important problem. And there are lots of interesting challenges there. And I will be happy to collaborate on many of these questions. Here are the 3 papers that I talked about. That's it. I will end here. Thank you.
Thank you, Amit, for this very interesting talk. Do we have questions from the audience? Let me see. I do not see any. So nobody's written one, but
so yeah. I have a question, Amit. So when you look at, I mean, because it sort of spatially, so there was this connection that Vineet made about explainability and robustness. What kind of explainability? What I mean, so if I look at, say, equivariant model, and I try to explain why it has classified a certain way. I mean, are there good explanations known, excepting for what we believe are good explanations for such models?
Yes.
And
currently, sorry, you go ahead. Do you have?
Yeah, so that is the first question. And then, I mean, is there a sort of, just like he was actually in his talk, he talked about using saliency maps as because saliency maps are some kind of explanation. At least we believe there's some kind of explanations. So are there, if there are similar things, can one use those to get equivariant sort of models which are robust to those kinds of transformations? If one has has a notion of explainability of those features learned, can one sort of?
Yes. So one of the things is these saliency maps, or there are these feature-based attributions which give you local explanations about the prediction of a model on a given input. They are not global explanations for the global behavior of the model, even though this, say, equivariance or invariance to certain kinds of perturbations, that seems to be like a global property that you want. If you want these feature-based attribution maps, they are sort of local explanations, but they might still be helpful in the sense that sometimes people want that the model is not really learning some spurious correlations. And there, some of these like feature-based attributions might be helpful, but I don't know how to think of these feature-based attributions.
Maybe
for a global property, such as, say, equivariance or invariance.
I think that I think there is a response to that, Amit, unless I completely misunderstand, in the kind of work that Joao's doing, because when you have a logical proof, right, of a certain set of features, and it's a minimally sufficient set of features to entail the prediction, that is in fact, or features with their values, that doesn't, of course, necessarily describe, and typically won't describe just one instance. And so it does give you an explanation of the global behavior of the algorithm, because you know all the points that have this minimally sufficient set of features, they will have entail this prediction. So I mean, it's more than just a local one. Yeah, I had several questions. I guess we also now have our general discussion session, KV. So we're in that. What I wanted to ask a little bit about how you saw the connection between the two parts, Amit, of your talk. So what I got is that, yes, okay, so we have tensions between individual fairness and group fairness. We have these tensions between spatial robustness and adversarial robustness. Do you really think it's the same kind of phenomenon, or is it just a structural parallelism that you feel where you feel that we might get a nice balance between individual fairness and group fairness using some appropriate kind of training, like you did in the group in the spatial and adversarial robustness case?
So some people do think of group fairness as some kind of adversarial robustness, where you perturb only the sensitive attribute and the prediction should not change.
Mm-hmm.
So in that sense, like this adversarial debiasing that is done for group fairness, that is very much parallel to adversarial training.
Mm-hmm.
So there is a clear parallel between, say, group fairness and adversarial robustness. I don't know if there is something similar. In fact, I doubt if there is anything similar between, say, individual fairness and spatial robustness.
Right. Okay. I see. Okay. All right. Thank you. Well, I have one other question about the spatial robustness, and this involves, so Vinesh's work and KV's work and you. So it's a question of all three of you. Aren't these spatial transformations kind of hard for humans after a certain point with when you're rotating things around? And isn't the human response different to these two kinds of perturbations? We don't notice the adversarial ones, or we think they're irrelevant and silly. And the spatial transformations we find to be rather difficult cognitively. Or am I just mistaken about that?
I didn't understand the part about why spatial transformations are difficult for humans. I thought spatial transformations
I thought it was just something empirically given that we're okay at doing some of these rotations, but maybe not all of them. I mean, it's sort of a restricted competence, or maybe I'm wrong. Maybe humans are good in group in spatial transformations. What is the data on humans and spatial transformations and spatial robustness? Are we really good at? Is our classifier spatially robust? Let me put it that way.
So what do we mean by spatial? Do we want to go all the way to, say, captchas?
I thought arbitrary rotations and let's just look at the rotation group. So arbitrary rotations.
I think we're good at it. I mean, that's what I would suspect.
Okay.
I mean, unless there is a lot of sort of invariance already in the object, and I mean, like a 6 and a 9, perhaps. I mean, but otherwise, we are fairly good at it, I think. No? I mean,
okay.
I've never asked this question myself, but
yeah. Okay. No, I was just wondering, because I'm thinking, we're seeing a sort of it's something that, if you've been worried about adversarial examples and sort of lack of good performance on a classifier or some kind of ML system, we always think it's a kind of question of training, right? So if we just did the right training, we would get it. I'm just wondering, do we know that in fact to be true, or is it really that sometimes, and this goes back to some of the talks in the first session, that maybe it's because of some of the intrinsic structure in the objects that give rise to the data that make us, and we're somehow attuned to that structure, that we get, it's not just a matter of training, it's a matter of sort of innate tuning. So this is a very old debate, but I just wonder, whether training is always the issue. And so I was trying to get at that worry by thinking about how we react to spatial transformations versus adversarial transformations. This question doesn't have an answer. I'm sure. Mandayam has a question. Yes, Mandayam. Sorry.
It was interesting that you said that you have some training methods that can preserve spatial robustness while also being good at adversarial, having the other adversarial purpose. Do you have training models trained models, I mean, that you have used in your technique, models that you have trained that are either just individually good at preserving spatial robustness properties, and also, fairly accurate in preserving both those properties. The reason I ask this is for like a selfish reason. We have some logical methods we've been working on that are good at given a model, a neural network model, that we can use it to verify the spatial spatial robustness property. Okay, there are other people that are doing adversarial robustness things, and we have had trouble getting some models that are preserve spatial robustness. So that's why I'm asking what kind of models that you have actually used your training methods, and if we can have access to those models that you have produced.
So we don't have any special models. We basically, for our experiments, we looked at first the two extremes. One is like the typical models that people use for adversarial robustness, which are just adversarially trained models. And the other extreme, which is group equivariant, so rotation equivariant models that are, or translation equivariant, so standard CNNs or GCNNs, where these are rotation equivariant, trained with progressively larger transformations to make them spatially robust.
Yeah, but you must have done some experiments, I presume. So do you have?
Yes.
Can we have access to those models?
Sure.
That's the question.
Sure. So what we proposed was just a method so that both of these can be adversarial training and this training augmentation with larger spatial transformation. They can be done gradually, so as to avoid this trade-off or the effect that you get either only adversarial robustness or only spatial robustness.
Yeah, I understood that. Both. So I'm interested both in access to your whatever algorithms they are implemented for training, and if you do have certain models on which you have experimented and that are really available, that is also would be useful. Yeah.
And can I just ask a very quick follow-up question before we move to the next one? I mean, was there any degradation once you did this combined training?
So degradation is, so what we think of these as, like, we want Pareto optimality. Now you might say that both extremes are also Pareto optimal in like by the definition of Pareto optimality, but we want kind of Pareto optimality where ideally we would like both to be like as good as getting. So ideally one would like a model that has adversarial robustness and spatial robustness, both as good as what we would get if we had optimized just for one of these. Right. But in our paper, we have a theorem which sort of rules out this possibility. Like it says that there is a trade-off, and the trade-off is like unavoidable. You can't have, like, one can create a distribution where you cannot have both of these high.
Yeah, that's what I thought. I mean, and that's something that we see time and time again with these different training regimes, that we overfit in when we're trying to do this adversarial robustness training, and yeah, okay. Thank you.
What we have is just an extension of the already known trade-off between generalization and adversarial robustness.
Okay, thank you. Purushottam, you have a question or a remark here.
Yes. Yes, so this trade-off may be relaxed if we focus on, let's say, domains that are not as generalizable or imagine it, because humans, this is in response to the comment you made, Nicola, that the humans also have their limits to how much they can tolerate these spatial transformations, but on a small enough domain, humans can get crazy good. So it might be a domain specific thing for AI models as well.
Ah, okay. So we can specialize. We can also overfit to the data just as AI models do.
Yes, and it might be a controversial thing to say, but if the application is important enough, overfitting might not be such a bad idea.
Right. Okay, thank you. Okay.
Maybe we should just open the discussion and ask.
Please, yes.
Yeah. So I mean, so one thing that is expected. I mean, at least there is an expectation that there should be some kind of suggestions on what, based on what you heard so far. I mean, yesterday and today, if there are specific areas that one could potentially look at for collaboration and so on. So if based on what you heard, if you would like to say, I mean, anyone is welcome to say, to speak out and express their views, because finally Nicholas and me are supposed to actually sort of write down and say, okay, this is, we have to give a summary of the discussion in some sense. So yeah, so my so actually based on something that Nicholas, you asked yesterday, you asked of when Hari was talking, you raised this question of whether one could actually look, but one, I mean, I'll just take 2 minutes and say what I felt was a possible sort of thing to do. It just came from what you said, which is you take NLP models and then you look at their word-like embeddings, perhaps, and you construct some kind of manifold out of those. And is there a sort of small sub-manifold which actually describes that? I mean, now I don't know whether this question makes sense. First experiment, perhaps. I don't know, but that's a reasonable question to try on your NLP. I mean, of course, it has to be domain specific, but so is manifold learning. I think. I mean, they are really talking of three-dimensional images of some molecules and so on, and then you get this image, and you're trying to reconstruct the manifold with noise. I mean, perhaps one could think of a similar question for NLP, but if you want to use those techniques, then of course you would have to embed it in some continuous space. And there is a natural choice actually, which seems to be good. At least NLP seems to perform quite well there.
Yeah. So that is an interesting question. I guess what struck me about, and this also came up a little bit in Vinesh's talk, is that, we've been working with the people from ISI, Indian Statistical Institute, on this, that you know, the machines are very good at catching these statistical correlations, and as Vinesh said, not all of them are right, and there's something about the structure of the data that sometimes we miss, and we capture some of it with one kind of training, but then we miss another aspect. So what we really need to do is get at that structure. And I was just thinking that, yes, that manifold hypothesis is one way of thinking about getting that structure, but the structure is complicated, and it does have something to do with spatial robustness that you folks have been working on, because what we seem to miss is that, you know, this notion of an object with stable properties that are, you know, and these things are invariant under certain operations, though not on others. And this is part of something what you might call a grammar. Well, I mean, there is grammar, which defines and the semantic grammar, the logic of an NLP text or message, defines that structure very precisely. We have a very good idea of what that is, and we have a somewhat, well, at least I have a vaguer idea of something like a scene grammar provision, but I think it's the same thing, that there are objects there, they're, you know, and they also have properties that should be invariant under various transformations of the image. And it doesn't have to do with pixel values. It has to do with, you know, the physical objects that lie behind the pixels. And so it seems to me that somehow, if we really want to make progress on the three things that were mentioned in this seminar, which is robustness, but also interpretability and fairness or bias at the end, is that we want to somehow capture that structure. Very big open question is how you do it, but Hari's work, and I've read some of the Pfefferman stuff. It's difficult for me, I think, but I think that is one path to look at. I think Monday I'm also had another topic for working for some future work, which is it sounds like this idea of an abstraction would be very useful for Joao. And I mean, I also work on logical versions of explainability or interpretability. So we would very much like to see Mandayam, some of your work on that, and maybe you
I was just going to add a couple of points there. So yes, we have been looking at proving robustness and both this adversarial robustness and spatial robustness, and how to scale them for big networks, okay, using abstraction techniques. And what we have found is that these abstractions that we need to use are somewhat different when you want to prove spatial robustness as opposed to adversarial robustness. Okay, that is one thing. And there, I mean, in terms of collaboration that I'm thinking of, certainly, and I want to extend that to so there are two kinds of things, collaboration that I can see that I want to leverage. One is we want models and the training methods, etc., that other people are working on that aim at getting better handle at these preserving these properties and improving accuracy on these things. And then whether we could add logical techniques, complement those things with the kind of logical techniques that I use. That is one. Or another thing is with Marcus Silva, who has looked at more interpretability and explainability, and there whether the kind of abstraction techniques that we use for proving robustness can be used to scaling, because we also use SMT solvers and SAT solvers for in our work with linear programming solvers, and to some extent some non-linear solvers as well, because in our work we end up having to get into the non-linear domain as well. So yeah, those are things that I certainly interested in.
I just gave you my email address. Maybe Joao, you can type in your email address so that Mandayam can send us some of some pointer papers, or if
sure.
Yes, I can send some report of our recent work and the things that we have done and we're doing. Yes, certainly.
Purushottam, you have something to add?
So I don't want to unnecessarily project the work that I presented to the realm in which
no, but generally, anyway, you work on multifold things.
Right. So the area of interest in which the area in which I might have a bit of interest is what happens when these models are subjected to an extreme amount of diversity in the data. So that is to some extent already the case if our 10 and if our 100 and ImageNet are really diverse data sets. But one of the areas in which I work is in classification problems where the number of classes or labels is in the millions, and now we are going to hundreds of millions and billions. We find that several of the methods that operate not only in terms of prediction time and all, but also in terms of their performance on tail label, like tail difficulty or challenge in doing well on rare classes and rare labels is always a issue, even in these standard benchmark data sets, but it becomes really bad with millions and
What
millions
are the
of classes.
standard data benchmarks you have which have such large?
Yes. So I can send you a link to a repository where we have dozens of such benchmarks publicly available. We have several existing baseline methods that have been published in the recent years, both deep learning as well as classical non-deep learning style. This is an established area, but I think it has a sort of a disconnect with the areas which were focused on in the summit. So this area has much more application in the data mining, web retrieval community. So I would be happy to send a small compendium of resources which can maybe spur some interesting collaborations.
Purushottam, can I ask a question about this? So, I mean, you have, this is like a huge multi-classifier problem. You have 1 million labels. How much data do you have for 1 million labels? I mean, you know, we know that classifiers are really good once they get a lot of data for, not so many labels. So is it just a problem not having enough data, or is there something else going on?
It's a paradoxical thing. There are millions of data points, but for any given label, there might be only 2 or 3 data points, which is again not unheard of in CIFAR 10 and CIFAR 100. And this becomes interesting because questions of fairness and other things come into play very, very prominently, which is why Amit, so Amit knows about this work, I'm sure. But here fairness is more than just an effort to convince someone that the method is not biased or something. It has real business impact. Like if a advertiser doesn't get their ad shown because of biased behavior from the algorithm, the advertiser will leave the platform, and it's bad for the platform.
Right. Yeah, okay.
No, just a random thought. I mean, it might be completely random, so you can ignore it. But I mean, looking at, I mean, can one sort of think of this? But of course, in the framework that Mari was talking about today, which is somehow, I mean, expressing this whole business of being fair and so on in some logical framework, which I don't know. I mean, it seems to me, look, clearly fairness is something that you can capture in logic. It seems completely reasonable that you should be able to capture in logic. And but I don't know how to. Yeah, just some random connection, but I don't know. I just.
Yeah, so sorry if I'm interrupting, but fortunately in the setting, which in the very, very specific narrow setting in which I described the application, fairness is often a bit methodical and a bit easier. I'm not saying this is the only notion of fairness or this should be the only notion of fairness, but fairness can often mean make sure, let's say, coverage. At least every advertiser should get at least blah impressions, or else no user should see a blank screen when they visit the platform. So notions of fairness there become slightly simpler, but there are lots of issues that are unanswered in the extreme scale, primarily being calibration. So calibration is a very, very well studied problem in deep learning and traditionally as well. But at extreme scales, it becomes very expensive to perform calibration, even with the simplest of models. So what happens is that the ranking algorithms are able to, when working with these millions of classes, the ranking algorithms are able to nicely rank, or maybe not nicely, but they're able to give a ranking of ads or whatever, but they are unable to offer, let's say, confidence scores that can be trusted to say that, oh, here is where I want to cut off the rank list. I want to show, let's say, only the top 2 or the top 3. So that is a clear and present open problem in extreme classification.
So you should talk to Vianney about this, Purushottam, more. No, did you see links? I thought, I mean, his talk was certainly, it seems relevant to some extent, especially to this application that you're thinking about with ads.
Right, I agree.
So, KV, as a follow-up to what you just explained, I mean, you talking about extending Murray Christian's like approach to a more to formally or developing some logical framework for capturing fairness.
Yeah, exactly.
The fairness.
And this came from what Nicholas asked her, right? Because he was asking her whether, okay, there is this very limited viewpoint that, not limited, but there is that viewpoint that she has taken, and he was wondering whether it can be extended. So it seems
certainly as a logical formalism, that sounds very interesting to me. Okay, to explore whether it all depends on what other fairness kind of means. If it is like coverage kind of a thing, like what Purushottam just now mentioned, then I can see, okay, those being able to being amenable for logical characterization. But it is interesting to see. I mean, it would be interesting to see if some of those things can be captured, and whether the analysis can be then mechanized or not, using logical calculus. That's a separate thing, and then you get into all these continuous versus discrete domain and what kind of mathematics that you use. But at the formalization level, I feel like it.
Amit, you have anything to say? Zhao?
Yeah, I had another. Oh, sorry. Yeah, I'll be quiet. One other thing I thought of, but Dinesh is no longer here, is that he was looking at saliency maps, and I mean, you suggested a couple of other indices. One of the things that we could do is then translate. So a saliency map will isolate roughly certain feature values for a decision, for a prediction. We can check that with logic to see if the saliency map actually got a logically sufficient set of features to actually predict the answer. Maybe the set of features was redundant too, so we could get a more minimal explanation. It seems to me that one might, and if we can get these saliency maps relatively efficiently, or other indices for these large-scale networks, we could use this tandem of logical and more statistical techniques to scale up as well. This would be another way of thinking about Mandayam's and Joao's interaction.
Yeah, but here I think the problem is what Amit pointed out, that saliency maps typically explain a particular instance.
Yeah, but that's okay. That's okay. So one of the virtues of the logical approach, it seems to me, KV, is that you can give both something to explain the global behavior of a net. You probably need a lot of explanations, because there are probably many sufficient, minimally subset minimal sets of features that are sufficient to guarantee a particular prediction, and then for all the predictions, and there's even more. But you can also do this for a particular individual, right? You can look at the particular individual. What is the subset minimal set of features of this instance that generate the prediction? And there may be several, because that's something we know also from causal models. And there's a tight connection between causal models and logical models through the work of David Lewis and counterfactuals in the 1970s. But anyway, yeah, no, we can look at, so we can do this also for local explanations as well as global explanations.
Okay.
Sorry. So I don't know. I thought that might also be a interesting path of collaboration.
Okay.
Does that make sense to you?
Yeah. Amit, want to say something? What about the others? There are many other speakers who are, you should ask all of them to. And Nicholas, Jean. Mari wants to say something. Amit, you are here. Amit is left, is it?
No, I'm here.
Yeah, sorry.
Yes, I don't know what to say very precisely or constructively, but
none of us know.
I think that, yes, I liked, for instance, logical encoding, trying to logically encode for explanation proposed by Joao. For fairness, the logical specification of fairness, I think that it depends on what we define as fairness, because as it's not my topic, but when I listen to people explaining the fairness problems, they usually define it as an optimization problem. So try to minimize, to maximize the fairness and minimize, etc. So, and this aspect, I think it is difficult to this optimization problem setting. It is difficult to encode in logic.
Okay.
There I might, I know in general, I might, in general I agree, but some optimization problems, linear optimization problems plus logic, okay, you can do it. SMT solvers do that. I mean,
yeah,
can
that's true. That's true. That's true.
Where you will invoke, LP solvers.
Yeah.
And there are even nonlinear extensions if there are, like piecewise, even if they're nonlinear, piecewise linear, then you can always do it. So there are some interesting, but I think it is important to understand what fairness is. I mean, I didn't get, get a very clear understanding. Maybe not all kinds of fairness is possible to express logically. Okay.
Okay.
I'd like to understand more, like you said, about what exactly.
Okay. So I'm sorry, because I have to leave. I have to run to another meeting, and it is another building. So I have to leave. So I tell you bye.
Okay. Bye.
Thank you, Marie-Christine. Bye-bye.
Bye.
Okay,
Bye-bye.
thank you. Bye.
Yeah, because there are optimization problems with syntactic constraints that one knows are actually that can be solved reasonably well, actually. So something that Papadimitriou is, I remember from the 90s. I mean, I have very rusty memory of that now, but there are some interesting questions that he had actually on count. I mean, those are of course counting problems, perhaps not.
Yeah, but I think you can do a little bit more than counting, is what I'm saying. Okay? By embedding LP solvers within these logical engines. Okay? So it consists of being, I mean, it assumes that you could, if you could make multiple LP calls at different points.
Oh.
I don't know how well they scale up, okay? But certain optimization problems can be expressed as search problems with the repeated LP calls.
There is the issue of scalability. So with respect to Mandayan's suggestion, there is the issue of scalability. So that could be a problem. But I completely agree with Mandayan that we can model this optimization problem as a logic optimization problem and try to solve them as well.
Prashant, you have something to say?
Yeah, I work on topics which are a little far off from the others, I guess. I work on reinforcement learning, the gradients and such. I don't know how this works, but if somebody is interested, I'll be happy to talk. Of late, I just wanted to add that I've been looking at risk-sensitive reinforcement learning a lot. I also have a survey out there. It will come in foundation trends in learning sometime. So the question of risk and things like that, this is probably orthogonal to the discussion we had so far. But one thing that I've been focusing of late is trying to incorporate some notion of risk and do the optimization process without MDPs or with MDPs, either case. Okay. Even in classic machine learning problems, if you bring in, so this is not to be confused with the empirical risk. I'm talking about like risk measures and human attitudes and things like that. Like, like for example, I mean, the classic optimization process is geared towards, minimizing or maximizing some expected value. In many problems, you want some notion of risk. For example, if I retire and I have a lot of money, assuming, and I give it to an investment firm, and if they say that they'll, in expectation, they'll, get my portfolio to multiply 5 times, but there's a 5% chance that the entire portfolio is wiped out, then I'll be a concerned man. Something like that. Okay, so these are notions of risk. So the point is not just money, even when you're riding, right? When you're driving, maybe in Bangalore or in Chennai, the way you drive reflects your risk behavior. Like whether you take shortcuts, whether you take a longer route, hoping less traffic, these are risk attitudes. So things like that. So the point is, if I bring in a risk measure to the optimization process, and then everything becomes difficult. Estimation, you no longer have a sample mean, and then you want to optimize things like that. So these are problems I've been looking at. If somebody is interested, I'll be happy to talk about them. Yeah. Like I mean, the point is like in the expected world, there's just one expected value, but in the risk world, it's like there's no one amazing risk measure. There are like dozens of them. I don't know, but yeah, it's good for an academic area, but it's yeah.
Prashant, I not expert in this area at all, but in our institute, we have roboticists who are very interested in, well, I mean, they have terrible planning problems for their robot and optimization problems. They've just recently been able to solve, they have to do these things very fast so that the robot can plan its next move and not fall over and crash. And it's very expensive to fix the robot if it crashes. And so there's a lot of risk there. They have been interested in RL, and they're interested in integrating RL with a sort of a planning mechanism, because and I think they might be very interested in talking with you. And I've sent you the name of the oh, I didn't go, the one of the main people involved in the robotics and optimization.
Yeah, so the email ID is what you pasted, right? Yeah.
Yes, sir.
Okay. Yeah, so in robot, I think safety is a concern. So the risk is like it comes down to some safety requirement.
Oh, the risk is, I mean, they're terrible risks, right? It's safety, yes, for interacting with humans, but then just the risk to, crashing the robot. I mean, it's 100,000 euros, if you break your robot. That's not good.
Yeah,
for
that's also
researchers.
true. So yeah, so actually this notion of risk, I think is more pronounced when you have money involved.
There's a lot of money.
Most of my risk sensitive optimization papers, the motivation is using a monetary example.
Mhm.
Yeah.
But you can use other cases also, but it's like emphatic in the money case. Yeah. Yeah.
Correct.
Yeah, I'll just check. So how do we, so what am I supposed to do with this email ID?
No, you can just write to him and tell him that Nicholas
Yeah.
suggests you talk to him and then see where it goes. I mean, nothing.
Yeah, Pranesh, I'm going to see him. I have to leave here now because I have to go to another meeting. But yeah, I'm going to see him in half an hour, and I'll just say that you're working on this and
Okay.
expect a mail from you.
Sure.
Okay.
Yeah.
Okay.
Well, KB, I think we have quite a few points here. Maybe we should, close the discussion unless somebody wants to say something. We don't want to, tirer par les cheveux, as we say in French, pull by the hair.
So, I mean, I'm done. So, can I leave? Or,
Yeah, sure. So, yeah. So, anybody wants to say anything, or should we call it?
Last words. Okay.
Okay.
Well, I want to say thank you to everybody for participating. I think there was some really, a lot of very interesting ideas and a lot of things to think about. I think the workshops were very worthwhile. So, and thank you, KV, for.
Thank you, Nicholas. Thanks everyone for attending. And
Nicholas, can we have one more group picture, if you don't mind?
Yeah, there are not many of us left. Okay. All right. One more group picture.
Request everyone to go switch on the camera, please.
Yeah, thank you, everybody.
Yes, thank you.
It's done. Thank you very much.
Okay. Thank you. All right. Good afternoon to all of you.
Thank you. Thank you very much. Bye-bye.
Thank
See
you.
you soon.
Thanks, everyone.
Bye-bye. Bye-bye.
See you everyone. Bye-bye.
Bye.